fractions. This week we are in 5th grade working on number and operation, specifically with fractions. Just like in 3rd and 4th grade, fractions have a lot of information entailing, so we're going to take in a whole week just with fractions. And as you can see, within this domain there are many different standards that need to be covered. So we're just extending our knowledge from 4th grade into 5th grade and using still more diagrams and models. And I'm hoping that you'll see some models this week that you haven't seen before, and perhaps even some aha moments. So I look forward to hearing your thoughts on these things. All right, Rollo and Zeus agreed to train for a walkathon together. Rollo walked 2/3 of a mile. Zeus wants to walk the same distance, but the trail near his house is marked every 1/6 of a mile. Use a number line to show how Zeus can be sure to walk the same distance as Rollo. So here's Rollo's distance. I have a full mile broken into 1/3 pieces so that I can determine that 2/3 is 2 copies of 1/3. Zeus's distance, his trail is marked every 1/6 of a mile, so I have the exact same unit of 1 mile, except this one is broken down into sixths. So in order for me to go the same amount of distance, Zeus would need to walk 4 copies of 1/6 of a mile to be the same distance as Rollo. So then we ask ourselves, 2/3 equals how many copies of 1/6? Well, it would be 4 because we hopped 4 times to get to 2/3. Also, I can see that if I were to multiply my numerator and my denominator by both 2, I would also get 4/6. Here's a record of a class walkathon, distances for each day. Which students walked the same total distance? We're going to explore this using fraction strip models. So I'm going to pull up a fraction strip manipulative, virtual manipulative I should say, and there are fraction strips that you can print and color off on your own in our manipulative folder too if you'd like to have something tangible. Okay, so using one of the virtual manipulatives, I have the option of using fraction tiles, decimal tiles, or percentiles. So we're going to use the fraction tiles for now. As you can see, there's a whole unit and then broken into halves, thirds, etc. Alicia, her distance on day 1 was 2/8 of a mile, so I'm going to put 2 copies of 1/8 here. And on the second day, she walked 1/2 a mile. So now I'm going to put 1/8 plus 1/8 is 1/2. So there's Alicia. We also need Brad. He has 4/8 on his first day. This is also a great opportunity to use these because we can also see that 4/8 is also the same as 1/2. So when talking about equivalent fractions, which we're going to get to here in a moment, and then he walked 12/16. We don't have 16ths. We don't have 12/16, but we could do 6/8, 6 copies of 1/8. So I'm gonna bring out 6 of them instead to represent 1, 2, 3, 4, 5, 6. Okay. When I close this fraction bar, I'll be able to move them over so we can see them better. Connor walked 2/4 on his first day. 2 copies of 1/4. And on his second day, he walked 6/8. So more of them eighths. 1, 2, 3, 4, 5, 6. Dan walked 1/4 on his first day and 5/10 on his second day. 1, 2, 3, 4, 5 1/10. And Elena walked 5 1/10. 1, 2, 3, 4, 5, and then 3/4 on her second day. All right, so let's line these up and see who, oops, that we didn't need that one. Who walked, we don't need this one. All right, oops. All right, so we'll put him here, but we'll ignore him. Okay. Line them up a little better so that we can compare them. Notice when we move into 6th, 7th, and 8th grade and we start converting fractions to decimals and percents, it's already doing some of that for us that we can kind of get an idea of what those mean. Looks like we're already starting to match some of them up. It looks like Brad and Connor, even though their fractions are different, their combinations of fractions are different, they're still equivalent. The same looks to be true here with Alicia and Dan. We can see that 1/4 matches the same amount as 2 1/8, and 5 1/10 is the same as 1 1/2. Let's see if Elena matches anyone here. It looks like Elena is going to match and do the same distance as well as Brad and Connor. We see that 5 1/10 is the same as 2 1/4, and that 6 1/8 is the same as 3 copies of 1/4. So these fraction tiles, even though again that they're different measurements, at the end they're still the same length. So expressions with sums and differences of fractions can be written in different ways using equivalent fractions. So 2/8 plus 1/2 is the same as 1/4 plus 5/10. All parts of the equation are equivalent because the fractions have the same value even though they're using different pieces. So Joshua is on a team with Alicia and Dan, so they all walk the same distance. Choose 2 different fractions from the list below to write an addition expression that represents Joshua's difference. So I have 2/8 plus 1/2 equals 1/4 plus 5/10 equals what plus what? So looking at 2/8 is something that jumped out at me. I know that 2 copies of 1/8 is the same as 1/4. So that could be one of my question marks. Also, I see 3 copies of 1/6. That's equivalent also to 1/2. So we could use that one. And there are many others in our list that we could use too. This is just one example. Use 2 fractions from the list to create an equivalent expression to 3/5 minus 1/3. We will use our fraction bars to help identify which ones will work. So right now we have 3 copies of 1/5, and I want to know which one of those fractions in that box will work as the same as 3 copies of 1/5. Okay. Well, we first start off with 3 copies of 1/10. So 3 copies of 1/10. I'm just going to stick them right here on the top here. 3 copies of 1/10. Well, boy, that certainly is not the same. So the 1/10 is not going to work. 3 copies of 3. Well, that would be 3 copies of 1. Well, goodness, that's way too big, so those aren't going to work. 2 copies of 1/6. Oh dear, still not going to work. 6 copies of 15. We don't have 15ths, but let's do 6/10, see if that works. So 6, 2, 3. I think we found our correct one here. So 2 1/10ths is equivalent to 1 1/5. So 3/5 is the same as 6/10. Let's do the same for 1/3. So we'll put our 1/3 up. Is that equivalent to 3/10? Bring my 3/10 up here. 1, 2, 3. And still just shy. There's not enough there. Close, but not quite. 3 copies of 1? No, way too big. 2 copies of 1/6. By golly, I think we found it. So 1/3 is equal to 2/6. So we found that 3/5 and 6/10 were the equivalent, and 1/3 and 2/6 was equivalent. All parts of the equation are equivalent because the fractions all have the same value. We learned in 3rd and 4th grade that as long as our pieces are the same size, we are able to find their sums and differences. So we know that 1/5 plus 3 copies of 1/5 would give us 1/5 shaded plus 3 more copies of 1/5 for a total of 4/5. But if I wanted to find the difference between 2/3 and 1/2, we are not looking at the same units. These aren't the same size. So what we need to do is determine what that size might be. Because if I start at 2/3, having a full unit line, and I subtract 1/2 from it, I'm not quite sure what's in the middle there. Because they're not the same, we can't add and subtract them together. So we need to make their pieces the same size. What we can do then is notice the yellow marks. We can split them, the thirds in half and the halves into thirds, so that we create sixths. And when I create sixths, I see then that 2/3 is the same as 4/6 because the same amount is shaded, and 1/2 is the same as 3/6. And notice that we cut the thirds into 2, so we multiplied by 2. We cut the halves into thirds, multiplying by 3. And now we can take 4/6 minus 3/6, so 4 copies of 1/6 minus 3 copies of 1/6 to get 1/6. All right, let's find the sum of 7/9 and 5/6. We know that we can't combine these because we don't have the same pieces. So what size piece should we make so that we can compare them and use the same? Well, we learned from the last example that we can multiply both of our numerators and our denominators by the same number, and it is still an equivalent fraction. Just as a side note, that students are going to be practicing this over a long period of time, so they will naturally deduce the quote-unquote rule for how to make equivalent fractions on their own through many different examples that they're working through. So I know we're going through this quickly, but we are covering grade 5 in 3 weeks, where you have an entire year to cover grade 5 standards. So keep that in mind. I know that 9 times 2 is 18. Similarly, 6 times 3 is also 18. So our piece sizes would be the same. So I'll take 7 times 2 and 9 times 2, and 5 times 3 and 6 times 3. So we end up with 14 copies of 1/18 plus 15 copies of 1/18 for a total of 29 copies of 1/18. Yes, this is an improper fraction. However, let students be flexible with the way that they represent numbers. Remember, we say this is 29 copies of 1/18. We could say that this is 18 copies of 1/18 plus 11 copies of 1/18 for one whole and 11 copies of 18th, since we surpassed the unit mark by decomposing our numbers. Let's add 1/3 and 2/5 using an area model. So I have a unit box. Doesn't matter what size that box is, just that it's a unit box. And I've split it into thirds. I want 1 copy of 1/3. I also have another unit box the same size as the thirds, except this one is cut into fifths. And I need to shade 2 copies of 1/5. By having one unit going horizontally and the other vertically, we have created a 3 by 5 rectangle. So notice along the left is 3 units, or 3, and along the top is separated into 5. So if I create an equivalent unit fraction, still cut into thirds, and have the first row highlighted for 1 copy of 1/3, and I do the same with my fifths, I see that all together that I have 5/15 plus 6/15 for a total of 11 copies of 15. Using an area model is an extremely powerful model for the following reasons. It can be used to add or subtract any fractions or fractional quantities. It uses fractional equivalence, a common unit, and the same whole number thinking that we've used in the past. It parallels the steps and the standard algorithm for addition and subtraction by finding a common denominator. It is a powerful pictorial stage between the concrete and the symbolic stages. Let's add 3/4 plus 4/5 using an area model. So I have a unit box cut into 4 pieces. I want 3 copies of 1/4. I have the same size box, except this one is cut vertically into 5 pieces, and I want 4 copies of 1/5. By having one unit going horizontal and the other vertical, we have created a 4 by 5 rectangle. So the same amount is shaded. Now only I have 15 of the 20 shaded to represent 3/4, and I have 16 out of the 20 shaded to create the 4/5. So 15/20 plus 16/20 is 31/20. Now what we can do to show that this is one unit, note that each one of these boxes represents one unit. I created above another unit box, I shaded in the yellow, and I started moving my blue pieces to fill up one whole unit, and then the other box just using partial. So I see that we are able to fill in one whole unit plus a partial other unit 11 out of the 20. Understanding the procedures of rational number computation is a prerequisite to success in algebra. We should make use of explicit properties of operations that explain the exact computational process we are accomplishing with fractions and decimals. Let's ask why 5 copies of 1/9 plus 2 copies of 1/9 is equivalent to 7 copies of 1/9. It is because we break it down, decompose 5 times its unit fraction plus 2 times its unit fraction. Then we can grab the 5 and the 2 and multiply it by 1/9 since that is the common factor. Add our whole number pieces. So that 7 copies of 1/9 we know is 7/9. So we decompose the fractions into unit A copies of 1 over B. We use the distributive property to undo the common factor which was distributed. We added the whole numbers together. Let's review some meanings of multiplication and division. So multiplication could mean that we're adding equal groups, and division could mean equal or fair sharing. It's called the partitive concept. Further equal grouping or segmenting is the quotative measurement or repeated subtraction concept. Multiplication and division can be represented by increasing or reducing quantities, as well as moving from factors to products or products to factors. We can make numbers smaller by multiplying them by fractions less than 1. Use a number line to show that when we multiply 3/4 times 2, our product will be smaller than 2. We want to think of this as 2 copies of 3/4. So here's 1 copy of 3/4 plus another copy of 3/4, which brings me to 6 copies of 1/4. Which is the same as 1 2/4 or 1 1/2. Again, be flexible with the way you allow students to represent their numbers. Let's use a tape diagram to show 2/3 of 15. We think what is 2/3 of 15? So I have a bar strip or a tape diagram here that's split into 15 equal pieces. I'm going to break them down into thirds so that I have 3 groups of 1/3. I'm particularly interested in how many 2/3 is, so I then get to count 2/3 is equal to 10 individual squares. Ashley needs a rope for the tug of war that would be 1 3/4 times longer than the 12 feet of rope she has. Show the mathematical expression you would use to find the new length. Use a number line to show Ashley how you figured it out. So we could think of this as 1 3/4 times 12, or 12 times 1 3/4. So I have a number line. I'm going to choose to do an open number line. So the first option is taking 1 3/4 times 12. So I want 12 copies of 1 3/4. So I will continue 1 3/4 making copies of it until I reach 12 of them. So I know that 12 times 1 3/4 is equal to taking 12 times 1, the whole, and 12 times 3 copies of 1/4. And 12 times 1 is 12. 12 times 3 is 36 times 1/4. 12 plus 36 copies of 1/4 is the same as 9, so 21. We could also think of this as 1 3/4 of 12. One group of 12 is 12, and 3/4 of 12 is, so I'm going to let the entire tape diagram represent 12. I want to split it into 4 different groups. We need to know how many are in each group. Well, 3 would need to be in each group to build to 12. I particularly want 3 of them. So 3/4 of 12 is 9. So we knew that one group of 12 is 12, and 3/4 of 12 is 9, so 12 plus 9 is 21. Use a number line to show which product is smaller, 5/8 of 16 or 3/4 of 16. So I have a number line, and I have the number line built up to 20, but we only need 16. So when I look at 5/8 of 16, I broke down the entire tape into eighths. I want 5 of them eighths, which is equivalent to 10. I broke down my 16 using a tape diagram into fourths, and I want 3 of them fourths, which is 12. So I can see that although 5/8 appears to be larger because we have larger numbers, it's not always the case. So 3/4 of 16 is greater than 5/8 of 16. Multiplication can be used to scale down. Let's use an array model to show the product of 2/3 and 3/4. So I have my model going vertically and horizontally. I have it broken to thirds and fourths. I want 2 copies of 1/3 and 3 copies of 1/4. What I'm going to do is overlay them on top of one another so that I get the same unit except it's broken to thirds, a 3/4. Notice that the color which is overlaid is their actual product. So we now have 12ths, and 6 of the 12ths are overlapped and shaded. So 6/12 is also the same as 1/2. This is a great stepping stone. As students work more with this model, they will be able to generalize the relationships between the numerator and the denominator. Naturally, students will be able to generate the rule itself, that when we multiply two fractions, we multiply straight across. We just went over a couple multiplication problems, but just with adding and subtracting, understanding the procedure of why the rule works will only enhance a student's success in algebra. So we'll go over why is 3/4 times 5/7. Why is that 15/28? So we can decompose the numbers. 3 copies of 1/4 times 5 copies of 1/7. Using the associative and commutative property, I can rearrange these because it doesn't matter in which order we write multiplication, it all equals the same. So 3 times 5 times the unit fractions, and we get 15 times 1/28, which is the same as 15/28. So all in all, we decomposed our fractions into A copies of 1/b, the unit fraction. We used the commutative and associative property of multiplication to reorder the factors into whole numbers and fractions. We used multiplication of whole numbers and used operators to reduce the unit fraction into 4 times smaller 1/7. Which volunteer is correct? Use area models to show the volunteers who will have the most grass to mow. So Susie is mowing 2 different small dog play yards that are measured in feet, 3.5 by 4 3/4 and a 3 by 6.5. Doug is mowing a large dog play yard that is measured in feet, 3.5 feet by 10.5 feet. So let's start with Susie's small yard. So we're going to create an area model. This is nearly identical to the area model that we used in 3rd and 4th grade. except we'll break them down into whole pieces and fractional pieces, and then we can multiply each separate area. So we'll start with 3 times 4 is 12. 3 copies of 3/4 is 2 1/4. Half of 4 is 2, and half times 3/4 is 3/8. Then we can add all of our pieces, 12 plus 2 plus 2 1/4 plus 3 1/8, using our rules of fractions, and we'll end up with 16 5/8 square feet. The other area is a 3 by 6 1/2, so our whole number pieces separated from our fractional pieces, decomposing them. So I just have 2 areas that we have to multiply. 3 by 6 is 18, and 3 times 1/2, or 3 copies of half, is 1 1/2. Adding them together, 18 plus 1 1/2 is 19 1/2. Now let's move on to Doug. Doug has a larger dog play area that is 3 1/2 by 10 1/2. And again, we'll separate them, decompose them into whole number pieces and fractional pieces. 3 times 10 is 30. 3 copies of half is 1 1/2. 10 copies of half, or half of 10, is 5, and half times half is 1/4. Adding our pieces together, 3 plus 1 1/2 plus 5 plus 1/4 is 36 3/4 square feet. Susie will mow a total of 16 5/8 plus 19 1/2 square feet for a total of 36 1/8 square feet, where Doug will mow a total of 36 3/4 square feet. It looks like Doug will mow a total area larger than Susie. So we can multiply fractions and mixed numbers in the same way that we multiply whole numbers to solve problems. Abigail has detergent and softener for laundry. How many loads of laundry can she wash with both detergent and softener? And how much will be left over? Detergent comes in a 160 fluid ounce bottle, and 1 laundry load is 1/3 of a cup. Softener comes in 96 fluid ounces, and each laundry load needs 1/6 of a cup. We need to know how many cups of detergent that we have. There are 8 fluid ounces in 1 cup. So 160 fluid ounces divided by 8 fluid ounces is 20. So there are 20 cups in a bottle of detergent. We want to know how many 1/3 cups are in 20. So we can use a bar model. I start at 20 because that's when it's full. There are 3 1/3 cups in a whole cup. So since there are 3 1/3 cups in a whole cup and we have 20 cups of it, we'll be able to take 3 loads of laundry for every 1 cup of laundry detergent. So she can wash 20 times 3, so 60 loads of laundry. Notice we started with 20 divided by 1/3, and it ended up turning into 20 times 3 to get 60. We now need to determine how much softener we have. Again, there's 8 fluid ounces in 1 cup, so 96 divided by 8 is 12. So there are 12 cups of softener. So we need to know how many loads of softener can we do with 12 cups if each load takes 1/6 of a cup. So there are 6 1/6 cups in each full cup. So if we have 12 of them, we will be able to do 72 loads of laundry. So 6 cups times how many cups we have is 72. So the detergent, we are able to do 60 loads, and the softener, we are able to do 72 loads. So she has enough to complete 60 full loads of laundry with 12 more extra washes with the softener. The meaning of division is the same with fractions as it is with whole numbers. How many 1/4 scoops of bleach are in a 12-cup container? Use a visual model to explain your answer. Pause the video, see if you can do this on your own, and we'll come back together. So I know that there are 4 1/4 cups in a whole cup. So each little bar represents a fourth of a cup. 12 divided by 1/4 is 12 times 4, which equals 48 scoops. Based on the reports, determine how much snow each mountain had before melting. Which mountain had the most snow? Let's start with Lolo Peak. 3 feet have melted. This is a fourth of what they had. So a fourth of, we're not quite sure, is 3 feet. Using multiplication and division relationships, we can also write this as 3 divided by 1/4, which we know is 3 times 4, which is 12. I want to know how many 1/4 can fit into 3. 2 feet are left at Trapper Peak. All but an eighth of what they had has melted. So an eighth of what they had is 2. Using our rules, 2 divided by 1/3, or how many 1/3 can fit into 2? I'm not sure why it says 1/3. It should be 1/8. Typo on Mrs. Richmond's part here. So 2 divided by 1/8 is the same as 2 times 8 because there are 8 1/8 per foot, but we have 2 of them. So 2 times 8 is 16. Mount Sentinel had 5 feet is melted. Now there is 2/3 left of what they had. That means that we have a third divided by what they had is equal to 5. So this is slightly different than the other two based on the wording, which is the same as 5 times 3, which is 15, because there are 2/3 left that we need to find, and if each third is equivalent to 5 feet, we would have 15 altogether. So taking a look at where the snow first started, we have 12 feet for Lolo Peak, 16 feet for Trapper Peak, and 15 for Mount Sentinel. Trapper Peak had the most snow. We can use the relationships between multiplication and division to solve problems with fractions. The relationship between multiplication and division holds with fractions as it does with whole numbers. Are these the same? Is 18 divided by 3 the same as 3 divided by 18? When I look at my first piece, I have 18 divided by 3. That means that I want to take 18 whole pieces and put it into 3 different groups. However, 3 divided by 18 means that I want to take 3 wholes and partition into 18 portions. Let's show 1/3 divided by 5 using a number line. Here is our number line. I have from 0 to 1 marked off in 3 different pieces, so the piece that we see is the 1/3. Now we need to take 1/3 and divide that into 5 pieces. We need to know how many of the cut new little pieces it takes to make a whole. I see that it takes 15 of them Therefore, 1/3 divided by 5 is 1/15. Let's show the reverse. 5 divided by 1/3 using a number line. So here I have 5 units on a number line. I want to ask how many 1/3s are in 5 holes. So we cut each hole into thirds. I see that it takes 15 1/3s to make 5 holes. So there are 15 1/3s in 5 holes. Therefore, 5 divided by 1/3 is 15. We used our understanding of division to interpret the dividend, divisor, and quotient in the division equations. The meaning of division is the same with fractions as it is with whole